Sparse Recovery, so there's a lot to tell you guys. Last time we introduced Sparse Recovery as a problem, and we started to prove basic facts like, when is it hard, when is it easy, in sort of simple ways. But then we saw a sort of more enlightening case where there was uniqueness that held. So we talked about, for example, uncertainty principles for incoherent dictionaries. And then we used those uncertainty principles to prove they were tight, but we used them to actually show uniqueness in some interesting range of settings. So today what we're going to talk about is one of the many algorithms for actually recovering a sparse solution under conditions like that. So we're actually going to show that the algorithm works. There are many such algorithms. This is, I think, the simplest one to analyze. So the one that we're going to talk about today is called orthogonal matching pursuit. Oftentimes you'll see this abbreviated as OMP. It was introduced in a very influential work of lec13 and Zhang. This will be also a very simple algorithm to wrap your heads around because it'll be just a greedy algorithm where you try and pick out which of the columns that should be used in your sparse representation greedily. There are many variants of this sort of greedy pursuit type of thing. The only differences are how you actually correct for the residual error after you've chosen one of the columns. That there's slight differences there, some of which are faster than others but lead to slightly worse guarantees. And then there are very different types of pursuit algorithms based on things like L1 minimization. So what I'm going to do is I'm going to introduce orthogonal matching pursuit. We're going to prove that it works. And then I'm going to introduce what L1 minimization is and tell you some of the basic theorems you should know there about like the restricted isometry property and so on, even though we won't prove them because that would take us probably a couple lectures to go into it. But all those things are in the notes from last time, so you can check those out if you're curious. So let's do orthogonal matching pursuit. So in OMP, what we're given is we're given some linear system and some target sparsity bound. So we're given some dictionary in m by n. And remember, n is always much less than n in our setting. So we're interested in recovering sparse solutions to linear systems even when A doesn't have full column rank, which was the case we talked about last time where A does have column rank. You can just solve the linear system and ignore the sparsity. So we only care about n much smaller than n because we want to actually use the sparsity in a beneficial way. We want it to be an underdetermined linear system. You also have your constraint vector. So this is some m-dimensional vector. And we're also going to have some target sparsity. So just some upper bound on when you should stop using this greedy selection rule. And the goal is to output some solution, x in Rn. Now the basic way that this is going to work is you're going to initialize a few different quantities. So you're going to keep track of what your current linear combination is so far. So x0, all you can do is you're going to set it to 0 at first. You're also going to keep track of the residual, which at this point in time is itself just the entire vector b. You just take, maybe it should be the other way around. Well, it doesn't matter, but let me just state it the other way around. B minus A x0. So initially, of course, this is just B because I've explained none of my input vector. And then what you're also going to do is your notion of progress is really a set of indices. These are the columns which you think should be used in A. So you're going to make progress on that, but you're going to start off with the empty set. And the goal is to build up this set in a way that you never add a column that's not in the true planted solution, but you always add something which is, and you sort of greedily make progress towards getting it. So the way that you're going to do this is you're going to run for k iterations, because that's your sparsity bound. Some cases you might stop early if all of a sudden your residual is just 0, even though you haven't reached k things you've used. And what you're going to do is you're going to choose the j, so the column that maximizes the following one. The inner product between aj and your current residual normalized by the norm of aj. And actually, in our setting, we'll only care about the columns being unit norm. After all, in the situations we care about, if you're given a different a, you could just rescale it. And it's not going to change the, that way you'd have to rescale your planted solution too, to preserve what your right-hand side is. But you're not going to change the number of non-zeros. So I'll state it this way, but throughout, we're really going to be talking about unit norm columns for A. And then what you do is you just add J to S. So very simple, greedy selection rule. Pick the column which makes the most progress in explaining what your current residual is. Like it actually allows you to reduce its norm the most. But the key point in all of this is now how are you going to update your residual? So orthogonal matching pursuit is a sort of more lazy way to update your residual. Because what you do is you set your new residual equal to some orthogonal projection. So right now I've chosen the columns in S. So all I'm going to do is I'm going to look at the subspace spanned by those columns, and I'm going to project B onto the orthogonal complement to it. And the last thing I want to say is that if RL equals 0, then you're just going to break this loop. So if all of a sudden, before you even reach some target sparsity K, you've explained away all of your right-hand side, you just stop there. And the final thing that you do is you just solve for excess, where you look at the linear system restricted to the columns you've chosen. And then you output x that you get from that, and x is 0 outside of S. So it's a very simple rule. The way to think about this step is really whatever residual you've already made it perpendicular to all of the columns in A, before you added J to the set. So really what you're doing is you're doing a type of Gram-Schmidt procedure to implement this step, where you then explain away whatever extra degrees of freedom you get by adding the new column into the set. So there are a lot of variants of this basic type of greedy thing, because some of the variants, what they do is, this is the type of step which is a little bit more computationally expensive. It'll allow us to prove better sorts of guarantees in terms of the constants. But some of the things that people do in practice is they instead just take the inner product between these two and use that to be the coefficient, which you then multiply by AJ to subtract off from the residual. So you can think about it as in the setting where these columns in A are pretty close to being uncorrelated, then just the inner product between your residual and the remaining column is a good proxy for what you should scale this column by and subtract it off from the residual to make it orthogonal to the new space. It's not quite perfect, but it's a lot computationally cheaper to do that. But does this algorithm definition make sense? So it's very natural, I think. But any questions about it? Make sense? All right. So we're going to prove one main theorem today. It has, I think it's a pretty intuitive theorem, but it has a few different parts. So it's a clever theorem. So let me state the theorem. Let me just state it this way. So we output x, where xs bar is 0. So we zero out all the other coefficients in it. So the main theorem that we're going to work up towards is the following. So of course, we're going to need that A is mu incoherent. those are the types of conditions we've used to show that there is a unique solution. So it's natural to impose them in the algorithms we're looking for, that the algorithms will be able to exploit them in a similar way to how the uniqueness principle did. And what we're going to do is we're going to assume that there's some planted solution, x hat. And what we're going to require is that its number of non-zeros be at most m over 2 mu. So this is the planted solution. And moreover, we want that our linear constraint comes from this planted solution. So in order to prove anything about this, I need to make some assumption about where B comes from. After all, if B is arbitrary, why would this ever find a sparse solution? It wouldn't, right? But here we're going to assume that this B vector actually comes from our sparse planted solution, which we don't know. And we want to try and solve this linear system for a sparse combination. Actually, all of the results that I'll be telling you about today, they can be generalized to work in the presence of noise. So instead of B is AX hat plus some small amount of noise, you can prove some guarantees about, if you have even sparser vectors, then you can recover something that's close to the true solution. But that'll just make our life more complicated to prove it, so I won't get into that right now. Then what we want to prove is that the output of orthogonal matching pursuits is exactly what we want. It's x equals x hat. So that's our main theorem for today. We're going to prove this. So one comment I want to make about this, right? So last time we proved an uncertainty principle for certain types of incoherent dictionaries, right? So does anyone remember what type of incoherent dictionary we proved them for? What was the restriction on them?
So we had 2 orthogonal matrices.
Exactly. So we proved it in a special case where we had 2 orthonormal bases. And for those types of incoherent dictionaries, we had our uncertainty principle and we derived a uniqueness principle from that. Actually, hidden in here is a different kind of uniqueness principle. This theorem already captures a uniqueness principle for more general types of incoherent dictionaries. The one thing to keep in mind is that when we talked about unions of orthonormal bases, we didn't have this factor of 2. The condition that we needed was we needed root m over mu, and we needed that the sparsity of the solution is strictly less than that. So here, actually, we're not going to be imposing any sort of structural assumption on what A is. It's just incoherent. It doesn't matter whether it's a union of orthonormal bases or it's has an arbitrary number of columns. That doesn't matter. But instead, we just pay this extra factor of 2, and then we'll be able to get not only an algorithm, but implicit in that algorithm is the statement that x hat is the uniquely sparse solution, right? So do you guys all see how this theorem implicitly is saying something about uniqueness? If there were another planted sparse solution that were as sparse as x hat and recovered the same B vector, then there's no way we could have a theorem like this. So we're actually going to see many of the same elements that we used to prove the uniqueness are actually going to come up in the proof of this theorem. So you should watch out for that, because that's even an immediate corollary of this, is a more general uniqueness principle. All right, so it won't be surprising that things like Grishkorin will come up again the same way that we used them last time. So just some notation, and let me tell you the basic outline for this. Because what I think makes sense is to understand the plan of action for how we're going to prove that this iterative algorithm works, and then to try and slowly fill it in, because we're going to sort of have a chicken and egg thing with how do we establish the invariance of this algorithm. But just some notation to keep in mind. We're going to set t equals the support of x hat. So t is itself a subset of 1 to n, which is just which columns are non-zero in the true planted solution. And what we really want to prove is we just want to prove that s at the end is equal to t. from that, it'll be easy to prove that actually if we found the right set of columns, we do find the right linear combinations and the right vector x. I'll prove that in a minute, but that's the main step, is proving that at the end, s equals t. And so that's our goal. That's our main goal, is to prove at the end, s equals t. And we're going to do it via the following invariants. So these will be our two invariants for orthogonal matching pursuit. Well, what we're going to show is that each index j added to s is in T. Yep.
So the target sparsity in this theorem is going to be just the platinum one?
So yeah, I guess so as long as you give me the correct upper bound, it'll actually work. Even if you give me a loose upper bound, which is like looser than, the target sparsity isn't really important in this. The target sparsity is actually more important in, that's a good question, it's more important in the noisy setting, where you have to know when to break. Because you don't want to spend too much time trying to figure out how to explain the noise, which you never really could. But in the noise-free case, you could really just ignore k, and you'll always hit that rule break at some point because of the invariance I'm about to describe. But that's a good question. So what we want to prove, the main thing is just that each index j that we add is correct, that it really does belong to T. Now, this isn't quite enough. The remaining thing we have to prove is just that, actually, can anyone tell me why this wouldn't quite be enough? We just proved each step you add the right index j. There's one more sort of fairly trivial thing that we
You
need.
can add the same index twice.
Yes. In principle, you could add the same index twice. It'll turn out from the way that we've projected things that that is not going to happen, because you would never get a gain from adding the same index again. You'll always be orthogonal to all the things you added, but I'll state that explicitly. We also want to prove that, each index j in T gets added at most once. That'll be a sort of very easy part to prove, but these two things will actually be interrelated in how we establish them. But this is the main game plan. So what this would allow us to do is each step we make progress, we add some index that's in T, and we don't keep adding the same index again and again. So finally we do get to the set T. And the remaining thing that I would have to show you, which I'm going to show you in a minute, is just that if we really do have s equals T, then we're actually going to solve for the correct x when we do this. Yep?
When we prove this, are we already assuming that it's unique, or are we also going to prove that?
We're going to prove, it'll be implicit in the proof.
So,
Yeah, we're actually not going to use that because after all, we haven't even established the uniqueness principle for this general type of dictionary, for just general incoherent without that union of two orthonormal bases. So the reason I'm not going to explicitly prove the uniqueness theorem for incoherent dictionaries is because the proof is basically this. I mean, it's just a little bit shy of it. And we've already done one uniqueness proof, so they actually have a lot of common elements to them. But I want to sort of emphasize how you can turn those uniqueness proofs into theorems for algorithmic versions. One more question?
To show that each index in T does get added to us?
Yes. Yeah. Yeah. We'll show all these things together with one common helper lemma, but you're right. And if some j in T, j not in S, then the residual is not equal to 0. So that's what we'll actually show. The real thing is we're going to show that if we have this property, then the residual is nice in that it's always supported by the columns of T. So that's the thing we're actually working up towards. Are there any other questions about this plan? So let me pick off the easiest parts of this plan first. So the easiest part is just, if we really do have at the end S equals T, why should we find the right linear combination? So why is finding the sparsity pattern enough to actually find the actual coefficients that you should use in that representation? So this is always standard that, sparse recovery is about getting the right support. And then once you have the right support, it's immediate that you actually find the right linear combinations. Because otherwise, the probability would be unique. But let's see the proof of this. So lemma 1. Is that under the conditions of the theorem for the sparsity bound we have for x hat, that in turn tells us how large T is, because T is just the support of x hat. Well, what we want to prove in order to show that finding its support is sufficient is we just want to say that that linear system where S equals T has a unique solution. So what we want to show is that AT, A restricted to the columns and T has full column. So that's the thing that'll allow us to use S equals T to prove the theorem. So any thoughts? This proof is pretty easy, so I'll open it up to the floor. Someone prove this for me?
Using the X is the sparsest solution here?
No, but we're assuming that the sparsity of x hat is at most that root m over 2 mu, and that B really, and that, that's what you need, and that A is incoherent. So, you don't have to give me the full proof, just tell me what the main tool we should use is. We've used this tool a few times by now. Yes, Gershgorin. Gershgorin is the answer I was looking for, right? So that's the sense, think about it, right? So, if A had orthonormal columns, then it would be obvious that, any submatrix of it is full column rank. And incoherence is just the relaxation of orthogonality that can possibly hold when you have more columns than dimensions. And it's the type of condition which tells you that things behave almost as if they were orthogonal. Not quite, but Gershgorin is the way that you actually prove that. That things that are uncorrelated behave as if they were orthogonal to a certain extent, right? So the proof, we've sort of done it already before, but let me just make sure you guys get this part. So recall that we've set T to be the support of x hat. And so we have that size of T is at most root m over 2 mu. And then what we consider, unfortunately I have to use different sorts of T's right now. So this is, we're indexing it by the set T. And I have to take the transpose. But hopefully you guys know what I mean by this. So I'm taking A and restricting to T, and taking its transpose. Sorry. But what do we get out of that? So that matrix is just a size of T by size of T matrix, in which we have ones along the diagonal, and off the diagonal we have magnitude at most mu over root m. Because that's the definition of incoherence. Incoherence was a parameter that's always at least 1 when you have more columns than dimensions. But in things like the spikes on science dictionary, it really is 1. So you get this mu over root m type of thing here. I want to caution you that in the notes, I think I defined incoherence as being the inner products between pairs of columns are at most mu. And here I'm actually saying that mu is defined so that the inner products are at most mu over root m. I think it makes it easier to parse what sorts of sparsity guarantees you're getting, even in the optimistic case, by defining mu in this way. So, mu is 1 is a really tight constraint. In any case, these off diagonals are mu over root m. And, hence, by Gershgorin, the eigenvalues, it's a symmetric matrix, so the eigenvalues are the singular values. Well, they're all contained in this disk centered at 1, because we have many different disks centered at 1 for each of the different rows. And the radius of this disk now is size of t minus 1 over mu over root m, because I have size of t minus 1 off diagonals here. So really in Gershgorin's theorem, I always have this union of disks, but here the types of disks that I'll use as my upper bound are all the same. So I get that all my eigenvalues are in this disk. And now plugging in what we have, so we have, t is root m over 2 mu. And then we have is that this quantity is actually strictly less than a half. And it's strictly less because we have size of t minus 1 in there. Right? So now, in fact, this is even a little loose because you would think that maybe I could have doubled the sort of, the sparsity that I can tolerate and still get some Gershgorin type theorem. But this factor of 2 really comes from, in order to prove uniqueness, you hypothesize two different solutions which have sparse supports, and you look at their Gershgorin things. So you really double the number of, things that you put in this grand matrix. See, this is the easy part, is once you found the support, find the coefficients. There you don't need that factor of 2. But in the proof of that theorem, we really do need that factor of 2, because we'll need to sort of hypothesize a different solution kind of thing. But in any case, all of these eigenvalues are contained in these disks, and hence this matrix, AT, T transpose, AT, has full column rank. Yes?
Can you say again, why is that radius less than 1/2?
Yep. So t, let's forget the t minus 1. Let's say it's t in here, size of t times mu over root m. So you agree with me that that should be the radius, the size of t minus 1 times mu over root m. Now if I, instead of plugging in, magnitude of t minus 1, if I plug in magnitude of t, then I have root m over 2 mu, and then times mu over root m, and all I get is a half. And it's strictly less than a half because of, the minus 1. So does this lemma make sense? This is an easy lemma. It's just that finding the support is sufficient. This is always, always true for sparse recovery, regardless of what setting, whether you're talking about incoherent dictionaries or RIP, which we'll get to later. But pop quiz, does AT have full row rank? No, right? Definitely not. The grand matrix we form by taking AT transpose times AT is itself a T by T matrix. We're saying that this rank is at least T, but AT is a matrix which is much taller than it is wide. So saying that the grand matrix has rank T tells you nothing about the row rank of AT. And it shouldn't, because really the number of rows will be much larger than its number of columns. Okay, so this really is a statement about the column rank and not the row rank. So be careful about that. Make sense? All right. So that's the easy part. So this I claim, let me state one sort of corollary of this lemma, just to sort of finish up the proof of the main theorem before we come back to proving those invariants. Those invariants are really the meat of the proof to begin with. This is sort of just the basic sanity check. But let me show you that why this is going to imply our sort of theorem. So the lemma, which is really simple, is just that if these invariants A and B hold throughout, and S equals T termination. Oh, sorry. S equals T termination. All right, so I want to say that the invariance would be enough at the end. So what we're going to do is we're going to suppose that at some intermediate step, we have S is strictly contained in T, and we know from B that then the residual is not equal to 0. But let's see, I want to say this. I want to actually prove sort of this part of B that I ignored, so let me state it this way. Let's ignore this part of B, and it's really going to come into the proof of this lemma. So we just have these two conditions that are each index j that's added in S really is contained in T, and each index doesn't get added more than once. So if we're at some intermediate step and S is is a subset of T because we know that A holds, but let's suppose it's strictly less. So there's some index j that's in T but is not in S. What I want to then prove is that the residual is non-zero. And the reason is if RL equals 0, then what it means is that we can write B as some AS times XS combination, but we know that B itself is also equal to AT times some X hat T, where by definition we've chosen T so that it really is the support of X hat. So every coefficient in here is non-zero. So what it means is that there is some J that's used in this linear combination that does not show up here. So we end up getting a linear dependence among the columns in T. Because even just restricted to the set T, we have two different linear combinations that recover the same vector. We could either ignore this index J that's in T but not in S and create the linear combination this way, or we could create it this way, or we could use it and create it this way. So what this would then imply is that AT doesn't have full column. Which of course is a contradiction with lemma 1. So that's the point, is just that we never have to worry about this issue. Yep.
So, but at this point, we are not assuming yet that X hat is sparse.
Nope. Nope. So all I'm saying is, there's this issue that, in principle, the thing that Blatzy mentioned is you could be worried about what if you stop short and you end up getting 0 residual error even before you've reached the full set, right? But I'm saying that that can't happen because if it did happen, whatever you take as your linear combination that's on strictly fewer columns, you also have a linear combination that uses, is a different linear combination of the columns of T, because there's some column that's used in this that's not used in the other, and then we'd have a contradiction the other way. So you actually don't have to worry that as long as A and B hold, you really are going to have S equals T at termination. There's no other way that you could break. And then we can use lemma 1 again and say because it has full column rank, there's only one solution, so we really do output the correct thing. So these are the things which just show that these are the right invariants to work with. And yep.
I think you actually prove B from
A. B will be easy anyways. So what do you mean I proved B from A?
Because if S is the proper subset of T, if we already know B, then they are
I'm not sure, because in principle you could still be worried about why doesn't that choose step pick out the same column again? So like A and B together are going to tell me that every time that I run run through an iteration of the for loop, I am adding a new index, which is pushing me closer to T. This is the lemma that tells you you can't really stop short of actually getting to T. And then, lemma 1 implies that once you have T, you actually find the correct linear combination.
B says that every index in T gets added at least once.
That's at most ones.
Oh, okay.
Yeah, but B will be easy anyways, but I think it's okay this way. Yep.
So in our case, we don't really run the algorithm with K, right? We just run it until we get 0.
Yeah, that's right. I want to state it this way though, because this is the version which you use when you deal with noise. But like this was Ariel's question, for example, K doesn't really matter, because whatever upper bound I provide here in this theorem, as long as K is larger than the sparsity, my break condition is not going to be reaching the end of the for loop. It's going to be the residual is 0. And we're only going to hit that really when we do have the correct set, regardless of what that is. But still, with the upper bound, that's the way you'd run it in the presence of noise. And there's actually a subtlety, which I'll get into more when I talk about RIP, that really all these theorems, I'm going to state them in cases where they have a truly sparse planted solution. But these theorems would only be interesting if you could extend them to cases where there is some noise. And there's sort of, last time when I taught this, I spent a bit more time on like Prony's method and stuff, because it's one of the sort of dirty secrets of compressed sensing that if things were exactly sparse, everything would be trivial. And what really makes it interesting is, also the robustness things. But I can get into that later. All right, so this is part 1. It's just why are these the right invariants? So there are any other questions about using these invariants to prove this main theorem? It should be clear now that if we can establish these, we're good. Right? All right, so now let's prove those invariants. And the way that we're going to go about doing this So the way that we're going to go about doing this is we're going to make use of some of the statal lemma, but really it'll be a helper lemma along the way that's going to give us the right answer. So this one. So these will be sort of 2 lemmas along the way. I'll state one is lemma 3, and I'll state the other is a helper lemma. So we want to prove we're working towards these invariants. We want to show that if at the start of some stage, S is a strict subset of T, then OMP selects J in T. We're not going to worry right now about proving that J is in T minus S. We're just going to prove that J is in T. And along the way, we're going to prove the following helper lemma, which is really the meat of the entire argument. This is the thing which makes the invariance work, is we're really going to assume, let's say, that if RL minus 1 is in column span of AT, so this is actually the main part right here. We just want to establish conditions under which we really are selecting something in T. Now, it'll be easy to show that we don't have duplicates in this. Now, lemma 3 is really just saying, something that you can prove inductively if that's true. Then O and P select some J and T. But it'll actually be easier to work with this type of lemma, which is really what the consequence of having this condition be true would be, is that the residual is going to be supported in the things we're looking for. So we're just going to assume that for this helper lemma. We're going to assume that RL minus 1 is supported in the column span of AT at the start of the stage, and we want to show that we pick out. Another way of thinking about this, though, is that at the very start, it's obvious, the residual is B. So it's obviously supported in AT in the column span. And you can think about this lemma as just saying, in the first step, why do you make progress and why do you pick some J in T? But the way I've stated this lemma, it'll actually be able to apply to all of the different stages in the analysis inductively, but you can think about it that way if you want for simplicity. So this is the main lemma. This will take us a few minutes, but then we'll be in good shape. So, how do we prove the helper lemma? Well, now let RL minus 1 be sum in J and T, Yj, Aj. So this is just by the assumption of the lemma that RL minus 1 is supported in the column span of AT. So let's write it out explicitly this way. And the same way, it's actually kind of funny. Like there are a lot of things that that are used in the proof of Grishkorin's theorem that sort of end up being used in the same manner in the proof of this type of statement. So, one of the things that you're going to rely on is we're going to reorder the Yj's such that, after all, there's no specialty to which order we choose the columns. Well, we're going to assume that Y1 is at least Y2 is at least, and so on, up to some Yk prime, which is strictly larger than 0. And then for Yk prime plus 1, they're all equal to 0. So all we're going to do is you have this purported linear combination of the columns in A, which I don't know. But hypothetically, what I'm going to do is I'm going to reorganize these Yj's. Now we know that there's at most k of them that are non-zero, because that's the size of T. But instead there could be even more that are 0, so we could have only k prime non-zeros. Let me sort them in this way. And now what we can do is what we want to prove, this is the key step in all of this, is we want to prove the following condition. We want to prove that the inner product between A1 and RL minus 1 is strictly larger than AI RL minus 1 for I equals 9 plus 1 to n. So there's something actually clever about what this intermediate goal is. So this will be our goal in this helper lemma. So imagine that the inner product between A1 and RL minus 1, we have all these unit norm vectors. What if it's strictly larger than the inner product between AI and RL minus 1 for I from K prime plus 1 to the end? Now, let me ask, let's do another pop quiz. So does this type of condition, if we can prove it, mean that we select A1? Shout it out. No, right? No? Anyone think yes? Don't think yes. Right? So all this is saying is that, you know, all these guys I really don't want to select. There's one guy who's dominated, who dominates them. I would never choose something in this set because this guy's inner product is larger. But it doesn't mean, for example, A2's inner product is even larger. That could be. But this type of condition, this is what's clever about this proof, is that this will tell us that we select some I in 1, 2, to K prime. That's what it'll really tell us, which is enough, because that's certainly in the set T. Okay? That's the main point. So now let's prove this part. And we're going to do it in sort of, you know, the obvious way. There's only one way to do this, right? We want to prove this type of strict inequality. Well, we lower bound the left-hand side, we upper bound the right-hand side. I don't know what else to do, right? So we're just going to take whatever this residual is, the way we've expressed it, and then we're going to plug it in, and then figure out what incoherence tells us as a lower bound for the left-hand side. We're going to take the same thing, we're going to plug it in, we're going to say what incoherence tells us as an upper bound for the right-hand side. That's all you can do. So this is the cleverness, and the rest of this is just following, you know, the natural thing that you would do. You know, there's nothing else you can do here. So let's lower bound the left-hand side. After all, they're only K prime non-zeros, and I've reorganized them so that they're in non-increasing order. And I just get this. Now, the sort of main point is that we take the first contribution, A1, we get the inner product with A1, we get 1. So we get at least Y1. And for all the other guys, the most we could possibly be subtracting off is for each one of them from 2 to K prime, we could be subtracting off Yj times mu over root m. Why? Because of incoherence. That's it, right? That's the largest that, for example, you look at A2, the largest his inner product could be is exactly mu over root m by the definition of incoherence. And then we choose whatever the largest coefficient, the magnitude of the coefficient, we subtract all those guys. That's the smallest this quantity could ever be. And now, of course, we can, in turn, we can, well, let me just write it out this way. Well, this in turn is at most y1 minus y1, because I could just plug in y1 for each of these guys, because they're in non-increasing order. And then we end up getting, K prime minus 1 mu over root n. Which now I claim, so we can just plug in things. Let me just write it out to be explicit. So we have y1 times 1 minus, and then we plug in the K bound, which we've had, which was root m over 2 mu. So I get that this entire thing is strictly larger than the magnitude of y1 divided by 2. Now, why strictly larger? Because in here, k is at most, k prime is at most k. I plug that in, that's fine. But then I still have this -1, so that gives me a strict inequality here when I actually plug in the k value. So that's fine. So that's lower bounding the left-hand side. Now, what else can we do? We upper bound the right-hand side. We do the same thing, right? What else can you do? So we have some general AI, where I is in this set from k prime plus 1 to n. And we look at AI inner product with RL minus 1. And we plug in, what it is. That's fine. And now we want to upper bound this guy. So in fact, the way that we can do this is we think about A2, right? We get an inner product between AI and A2. Now remember that this I, it comes from k prime plus 1 to n. So the largest these inner products can be, we have only the incoherence types of inner products. See, here we have one large inner product, and the rest were incoherence type inner products. Here we only have incoherence products, inner products. And then we can even just plug in y1 in here, and it's not a big deal. So we can actually upper bound these guys by y1 times summation j equals 1 to k prime of this inner product, AI, aj. And of course, now we can upper bound this entire thing by y1 times k, really k prime, over root m. And remember that k is this root m over 2 mu, so we end up getting that this in turn is at most y1 over 2. So this proves this inequality now, right? Because in here, we can just plug in magnitude of y1 over 2. We get that the left-hand side is indeed strictly larger than that, and the right-hand side is upper bounded by that, with it's less than or equal to that. So then that's the end of that limit. Okay? We prove this condition, and it immediately implies that we really do select some index in 1 through k prime, which certainly is in the set T. Okay? So this is the key point of the lemma. So that completes the proof of the helper lemma now. And now what I want to do is I want to go from the helper lemma to lemma 3. And then we'll be able to establish A and B easily. So this is just saying that we have this nice condition at the outset that RL minus 1 is in this column span. We're good to go. Let's actually weaken it to just this condition, which will be pretty easy. So we have, by assumption, that the set of, S, the set S that we've used so far to explain as much of our residual as possible, the subset of T, but is a strict subset. So now what we can do then is RL minus 1 is explicitly B minus its projection onto the column span of AS, which in turn is just sum over J in S of ZJ times AJ, where here we get these coefficients from projection. That's how we did it in OMP to begin with, right? So then it's easy to see that this B, this is a linear combination itself of AT times X hat T. So then it's immediate that RL minus 1 really is in the column span of T, because I've just written it in a way that since S is a subset of T, we're only using the columns in T. So this immediately implies that RL minus 1 is in the column span of AT. Does this make sense? So now, we apply the helper lemma. So the helper lemma said that if this condition is met, that RL is in the column span of T, then indeed we select one of the columns in T. And this just segues to the helper lemma. So we can just directly plug in the helper lemma, and we get our main lemma as a result. Okay? I see. Okay, good enough. All right, so now the last thing that I want to say is, so why does this imply the invariance we were interested in to begin with? There we go. Okay, so now the way to think about this is that initially we have the residual is definitely in rather, I guess we can think about it this way. So initially the S is the empty set, which is definitely strictly contained in T. So then lemma 3 implies that the first index we select really is in T. And then we still have that S is strictly contained in T. And we can apply lemma 3 again to say that J2 is also in T. And that's no problem. The only remaining part we have to prove is B now, that this process, what we did was we just set it up so that you always pick some column in T, right? Because you always have this condition until you finally get S equals T. As long as you're always contained in it, as long as you're a strict subset, you're going to be picking some column. And B is just finally going to tell us that this procedure does terminate and makes progress each time. It's never going to select something again. So the final step is that for B, the way to think about it is that if J is in the set S at the start of the stage, then we have that RL is by construction perpendicular to the column span of AS, which in turn implies that RL is perpendicular to AJ. And hence, whatever your current residual is, will have 0 inner product with AJ, so you would never select it. So that's the end. All right? So it's a bit of a long proof. There are a lot of, pieces to this proof. I mean, the main thing I want you guys to get out of this is that, first of all, in all of these sparse recovery things, you want to show that you recover the true support. After you have that you recover the true support, showing that you get the right linear combination is immediate. It just comes from the dictionary having full column span on those things that you've selected. That's the easy part. The meat of all of this is in showing that you actually get the correct support. And the way that you do it for something like OMP is you prove these types of invariants. You prove that every time you add something to S, it really is in the true set. And the way that you did this was this one clever, inequality here. The idea that you take, you reorder the YJs and you take one of them and you show that its inner product is strictly larger than all the guys you want to avoid. That's what allows you to prove the invariant, and then the rest is just showing that this invariant doesn't really get you stuck. That, first of all, you never have 0 residual error when you haven't found the full set T, and also that for each index J and T, you only added it most once, which is just explicitly true in OMP, because you would never get any gains to adding that back to the set. It's already in there. So are there any questions about this? All right, who's ready for more? Yes, all right, let's do it.
Wait, quick question.
Yep.
So the part that you erased in the invariant B, what was it? Why didn't it matter in the end?
So because I actually wanted to prove it.
But what was it? I forgot.
Yeah,
what it was.
So it was that if RL is not 0, then S is not equal to, S is not equal to. Oh, sorry. Yeah, it's like there should be an index J and T that's not in S. So we proved that because actually, if accidentally, we got to some intermediate stage where these two things tell us that, first of all, we always, add a new index that we haven't seen before, and everything we add really is in the set T. The other thing you have to worry about to prove that S equals T at the end is, what if you stop short? And there was like an element in T that you never got around to adding in S. That would happen if you broke the loop because your residual was 0. But the point is, you couldn't have explained all of your constraints B until you've recovered the full set T. So I proved that when I sort of showed that the full column rank of AT implies we get the main theorem. Yep.
Does this also imply that if K is smaller than what it should be, like it's optimal up to that point?
Define optimal up to that point?
Like if you have to choose less sparsity than what's optimal, then like, you get the best of the closest.
Yeah, I'm not sure about that. That's a good question. That's closer to the types of, can you prove variance of this theorem, which work in the presence of noise. Because when you give me too small a sparsity, then and you want to say something meaningful about how well you picked out, the best K part, then it's really like the rest of it is noise. So these types of theorems, it's super important that they can be generalized to things which are just close to sparse linear combinations. It's actually a sort of pet peeve of mine that compressed sensing literature doesn't talk about this better, because usually the sort of the standard intro for the slides is like, there's the Shannon-Nyquist rate, and I have to, if I have an n-dimensional signal, I need n observations, and look, we can get something that's much smaller than that, so we can go way below it. But the truth is that those things were known for about like 200 years, so it's called Prony's method, it's in the notes. But the issue is that Prony's method is really not robust to noise, and that's why you would never use it. So the real dialogue for compressed sensing is like, you take Prony's method, you take a log factor more measurements, and then it is robust. So I want to at least state, for posterity's sake, what RIP is. These are recovery guarantees that we talked about for incoherent dictionaries. But if you think about it, the type of sparsity we assume is, even in the optimistic setting, we have mu as 1, right? So sparsity, that we can tolerate is about root m. So if we have a k-sparse signal, how large we need to make m to be is about k squared for this. RIP is this, amazing set of techniques for getting m to be about k log n. K log n over k to be precise. I'll state that. But the truth is that if you only care about exactly k-sparse, you can get away with n equals 2 times k. It's just that that method is incredibly not robust to noise. So, just because I think everyone should know compressed sensing, let me state the things. You can ask me offline if you want to know more about RIP, and there are things in the notes that I think are quite good from the last time I taught it. So keep in mind, the goal in what I'm telling you about right now is how can we put stronger conditions on A so that instead of getting n as roughly k squared, we could get m as about k log n. So how can we do that? So let me tell you about the restricted isometry property. Who's heard of the restricted isometry property? All right, so we're going to say that A is RIP. It's also related, if you're a statistician, sometimes you'll call this a restricted eigenvalue condition. So it's a good way when someone talks about something to be able to pinpoint what community they come from, is like the way that they describe these types of conditions. There are subtle differences to them, but they're all about the same. I personally like RIP just because it has a sort of coding analog. A is RIP with some constant, delta k. So delta sub k, I'm going to emphasize that this is really, A is k RIP. This is how we want the A to behave on k-sparse vectors with some constant delta k. If for all k-sparse vectors x hat, we have the property that the 2 norms squared of A times x hat should be close to the 2 norms squared of x hat. Now it's not important, like I could put some arbitrary constant 100 and 100 here, as long as I put the same constant here. That's just the rescaling of the columns of A, it doesn't really matter. The important thing is that A should behave as if it's orthogonal on up to size k sets, even though the fact that it's has many more columns than rows. So now actually you can think about the things we prove for incoherence, the uncertainty principles, are really statements of this form. What they are is that they're statements like if A is mu incoherent, then A is k RIP for some k about root m over mu. That's the type of thing. But the truth is that if you generate A randomly, then it actually will have this RIP property for much larger k, much larger than root m. Now the challenge is that if you give me a dictionary and you ask me, is it incoherent, I look at it and I can tell you because I look at all the pairwise inner products and I figure out what the largest one is. But actually, even though we know random dictionaries are RIP, we don't actually know how to certify that a dictionary is RIP. So if you give me a dictionary and ask me, does it satisfy this condition for some large k, then actually it's, it very well may be a computationally hard problem, but it's still an open question of complexity to try and prove hardness for this problem. And in any case, so the main statements are that this property is really useful. So what do I mean by that? So it can be shown. If you want to see proofs, look in the notes. It can be shown that the output of the following convex program. So remember, at the start of the lecture today, I told you that there's, for example, orthogonal matching pursuit, and there are other sorts of greedy selection algorithms. And at the very other end of the spectrum are things like L1 minimization, where you remember the hard problem is putting L0 here. Find the sparsest solution to some linear system. Instead, if you put in L1, there's a lot of senses in which L1 is a good proxy for L0. So this is the type of approach that they use. They use this convex program, which you can clearly solve in polytime. What they show is that the output is exactly x hat. So you really do find the true solution if x hat sparsity is at most k, and B really is A times x hat. And you need some conditions on what this restricted isometry property is. So these are the types of conditions you can show. Is that if you have some restricted isometry property, you're starting with a k-sparse solution. Usually you need an RIP property on something a bit larger than k, so either 2 times k or 3 times k. So if those constants are reasonable, then what you can show is that this L1 minimization problem really does find the true solution. Now there's something that, so this is a lot of times the way you'll hear compressed sensing stated at, in sort of high-level overview talks. See, one thing I want to point out is that this itself is a really strong condition. Why should the B vector I'm given be actually a sparse combination of the columns in A? So that's not so clear. You might expect it to be close to a sparse linear combination. And the important thing about compressed sensing is that you can get guarantees which hold even in the approximately k-sparse setting. So that really is crucial. That's what makes compressed sensing interesting. So let me state the results. So let me introduce some piece of notation that we're going to need. Sigma k of x is the min over all w such that the sparsity of w is at most k of x hat minus w, the L1. So this, if you give me a signal which is k-sparse, sigma k of that signal is 0. The best k-sparse approximation is that signal. Now, if you give me something that's just close to k-sparse, so think about it as like there are k really large coefficients, and then the rest of the coefficients are pretty small. So that's not actually a k-sparse signal, and it's important that you can give guarantees that are meaningful in that setting. And what you instead do is you look at how good the best k-sparse approximation is, right? So this is, if you picked out, the best you can do here, if you give me some signal x hat, is you pick out the k largest coefficients and you leave the rest intact, you zero out the large ones. That's what this quantity would be. So it's something that's 0 for an actually k-sparse signal and is small for something that's approximately k-sparse in some way. And then what you can show, again, it can be shown you have a slightly stronger condition. So the output x satisfies something like x minus x hat. The 2 norm is at most c over root k, sigma k of x hat. So this is some notion of how close to k-sparse you are. If you had an exactly k-sparse solution, this guy would be 0. And you'd be saying that you actually recover the true solution. But in the sense in which, keep in mind, sigma k is measured with respect to the 1 norm. So this is often called, I always forget which direction it goes, like I think this is an L1, L2 guarantee, because you have an L1 constraint over here, and you have an L2 constraint is what you get. I forget which order the definitions go. And you're thinking about, if this were k-sparse, the 1 norm and the 2 norm could be off by about k. So this is the type of guarantee that you get. Yep?
So what we are relaxing is not this condition of the equality of observability, it's the sparsity that we're...
Yes, exactly. Exactly. So that's the interesting part, is we're relaxing the sparsity of these things. You can also get guarantees that work, in the presence of noise, where you then add some sort of, AX close to B, maybe in 2 norm or what have you. I mean, there's a whole area of these types of guarantees. Just to sort of complete the discussion, there are other guarantees you can get with L2, L2, L1, L1. Some of them are provably stronger than others. Some, there's a whole literature to these things. But the last thing that I want to mention is just something that I alluded to, is that if A is random, you think about it as being random Gaussian entries, that'll certainly work. Sometimes you can also choose it to be random plus minus 1s with a lot of zeros in the matrix, and you can choose sparse A's too. But the important point is that with M, which is the number of rows in A, about k log n over k, then you actually do get good RIP constants. You can get whatever sort of constants you want here, but this type of thing will suffice. So the important point is that in the case of incoherence, that was a setting where the m that you get is about k squared. It has the benefit that when you give me a matrix, like the spikes and signs matrix, I can look at that matrix, and I can check that it's incoherent, and then I know what sort of sparsity level I can tolerate. Now, compressed sensing, it's a sort of different type of way of thinking about the problems, because it's more interesting when A is not something chosen by nature, but it's something that you get to choose. If I get to choose A, I would choose it randomly, and then I would look at A times X, where X hat, where X hat is sparse, and I would look at my observed vector, and I'd be able to recover that meaningfully, even when my number of observations is only about k log n over k. So this, to me, is one of the crucial distinctions, is that these kinds of RIP things are much more appropriate when you get to choose A. The reason I wanted to spend more time on incoherence is because I think in machine learning settings, you don't get to choose A. A is some sort of intrinsic part of your problem that you want to learn or is part of your problem instance. And there, it's not so clear whether the A's are RIP. I think it's much clearer that they're incoherent. So if you actually tie this all the way back to this discussion of Logan's phenomenon, when we talked about the spikes and signs dictionary, I mentioned that the reason Logan studied that, so that has mu equals 1, so it's an incoherent dictionary, so we can get recovery about up to root m. And the reason Logan considered that, now we have algorithms for doing that, was because the types of things he was getting in Bell Labs were you input some sparse signal in terms of the numbers of frequencies you're broadcasting, but then the channel makes sparse impulsive corruptions. So what you're actually observing is a sparse linear combination of spikes and signs, and you want to know if you're given a signal and you know it is such a sparse combination, can you find it? Can you remove the noise? So that's a setting where actually the dictionary comes from the problem. The way that you've modeled the channel, the way that you've chosen the input to be only a few frequencies is the signs part of your dictionary, and the fact that your channel has impulsive events are the spikes. So this happens in a lot of settings in learning, that the way that you sort of think about what's the right basis is something that's intrinsic to your problem. Whereas if you get to design A, you can do much, much better, even though we don't know, given an A, to check whether it's RIP or not. So anyways, these are the important things to know from sparse recovery. We're going to talk about sparse coding next, which is where you think about A as something you don't know. You're given many examples of A times X equals B, so you're given B1, B2, and so on. And you want to find then, is there a common A that you can use to sparsely represent all of those observations? So that's a lot of times used as a model for learning, is that can I find a basis that enables me to compress? That's some of the intuition behind how the visual cortex is purportedly doing it. You had a question?
Do we have like same kind of robustness results for the first setting with the OM?
Yes, so you can prove robustness things.
You cannot, or
you can. In fact, so what I did the last time I taught this class was I showed Prony's method, which actually shows that if you take A to be the truncated DFT matrix, where you only go out to 2K rows, that actually given A times X, where X is really K sparse, you can always recover X exactly. But as soon as you add noise, you need the noise to be exponentially small, because the linear system is so poorly conditioned to have any hope of recovery. So the way to think about this is Prony's method has been known for 200 years. It tells you that in the exact case, you can get n equals 2k. Compressed sensing is really about losing an extra logarithmic factor, but getting things that work with this much more appealing robustness guarantee. So part of the reason I taught Prony last time was just out of annoyance that no one knew it. But I figure that's a bad reason to spend a class period on something. It's just out of tongue-in-cheek. I once gave a talk on compressed sensing where I started with, here are 3 things. Which of them, at least one of them, is false? There were common misconceptions, and they were all false. Because the answer was Prony's method for all of them. So just don't do that. And then I'm fine. All right. If you guys didn't pick up your homeworks before spring break, pick them up now. I forgot to give them back to you guys last time, too.
Quick question.
Yeah.
So maybe this is something I don't quite know, but when you use the L1 and you say it's a good proxy for the zero norm, in what sense is it a good proxy? In this sense?
In that theory, yeah. So there are settings which you prove other sorts of notions of proxy in statistics, in which the L1 is a good proxy. Sometimes there you care about how well you can predict A times X in the presence of noise. And there it serves as a somewhat good proxy, and it's a much better proxy when A is RIP. But the sense in which L1 is a good surrogate for L0 is always some RIP-like condition.
Okay.
That it allows you to do what you could do with L0 with L1, but only if A is RIP. That's the sense in which it's good.
Okay.